Okay, so the topics we are planning to cover are categories with families. So, and then extra structure, type former. So this is the notion of model of type theory. Okay, and this also includes syntax. So the syntax is the initial model. I will explain this, and then later we will look at some models. So the standard model or set model. Some simple models like the setoid model, pre-sheaf models. So there's a model for canonicity proof. So the canonicity model, maybe normalization proof. These are all different models of type theory, and they satisfy some extra stuff, and that's how we can export I don't know, function extensionality from this model, or normalization from this model, and so on. Okay, so I think we can start now properly. Okay, so please stop me anytime if you have a question, and I will upload this file somewhere. Maybe I will just add it to the Teams thing, so these notes will be saved. Okay, so the question is, what is type theory? So this is now, by type theory I mean dependent type theory. So it's this is a particular programming language, which can be used as a programming language and also as a foundation of mathematics at the same time. While some people refer to type theory as the study of type systems for programming languages, but we won't use type theory in this sense, but we will refer to type theory as this particular programming language. For example, Agda and Coq are based on type theory. Okay. And programming languages are usually presented by a BNF grammar. So, for example, say that a term in a programming language is either I don't know, lambda x.t, or an application, or I don't know, we have natural numbers, then we have zero and successor of terms, and so on. So, and then you have lots of terms, lots of different terms, and so such a definition is called an inductive definition. So it means that these terms are really some kind of formal objects. So all the terms are built out of these operators which are here in this grammar. So all the terms are if we have, for example, if we have this particular grammar, then all the terms are built from zero and then applying one of these three other operators on it, maybe multiple times. So zero is a term, then successor of zero is a term, then zero add zero is a term, then I don't know, lambda x dot zero is a term, and so on. So that's the general idea. And instead of following this idea, we will do this a bit roundabout way. So we will first define what is a model of type theory. Okay, so a model of our programming language, and then we will say that the syntax, which is the thing built out of these grammar objects, the syntax is defined as the initial model. So that means that a model such that there is a unique homomorphism models to any other model. So let me just illustrate this idea that this we go in step 1 and 2 with some simpler, much simpler language than type theory. So for example, natural numbers. Okay, so natural numbers are very simple because they are given by this grammar. There is 0 and successor of n. And then, okay, so instead of writing this, we say that first, a model of natural numbers. But please stop me if anything is unclear. So a model of natural numbers is the following. It's an n, which is a set, together with a z, which is in n, and an s, which goes from n to n. Okay, so a model of natural numbers is a pointed set with an endo function, and that's it. And now we say that the syntax, which we usually write n and 0 and +1, okay, is a particular model, okay, such that there is a morphism to any other model. Okay, so let's see what this exactly means in this simple case. So it means that we have a model. Let's call that model we usually call this model I because for initial models. Okay, so I is the initial model. So we have I.n, which is a set. We have I.z, which is in I.n. And we have I.s, which is I.n, arrow I.n, right? So, and this way, and now the real numbers, so 0 is given as I.z, 1 is given that as I.z, successor applied to I.z. And 1 can be defined like this, right? And so on. So this is how we can define all natural numbers. And what does it mean that there is a morphism to any other model? In fact, we need to say there's a unique morphism to any other model. It means that we have something called rec, which says that whenever you give an n, a z, and an s, so a random model, then rec will give us a morphism from I.n from I to this nzs. Okay, so we get the morphism from I to nzs, and this is okay. Maybe I write it like this. So we, for any model, okay, we get a function or a morphism from I to nzs. And what does this mean? What does this mean that we have a function, a morphism from I to n.s? A morphism has 3 components corresponding to n, z, and s. So the first component is rec.n, which will be a function from I.n to. Let me rename this model. Let's call the model M. Okay. So the recursor says that for any model M, I get a morphism from I to M. Okay, and then this morphism has 3 components. The first is a function, which is a function from any syntactic natural number to a natural number in M. Then we have the rec.z component, which says that if we apply rec.n on I.z, then we get M.z. Okay, and we have rec.s, which says that this morphism, this function, so the rec.z says that the function preserves 0, and rec.s says that the function preserves successor. Okay, so this says that rec.n, I.s applied to any syntactic natural number x is the same as M.s applied to rec.n of x, right? And in fact, just from and this is what is usually called, so the usual name for this thing is primitive recursion. So this is really just recursion on natural numbers, and from this we can define addition of natural numbers and lots of functions on natural number. Sorry, what's the
I have a question. Yeah, so but isn't that just what it means for something to be a homomorphism? I mean, everything about REC just says that it really is a homomorphism.
Yeah.
So how does it, like, how should we say, between any two models, like, this should be the case, right? Because otherwise it wouldn't be.
Yeah. So you are saying that this is the notion of homomorphism. Yeah. So
yeah.
There is a notion of homomorphism between any two models, but REC gives us a particular homomorphism between two models. So
maybe,
this is basically just the notion of notion.
You should notate the M in REC if you are defining REC here. So if REC has
so this is REC-M. Oh yes, sorry, I should have written REC-M everywhere. Yeah, sorry. This is the components of REC-M, right? Yeah. Okay. So the notion of homomorphism is here between I and M is given by this, but we do have a particular homomorphism. So there are lots of models between which there is no homomorphism.
Then maybe write the REC-M as well on after the colon.
Where? Sorry, which colon? This line.
Like after the colon, then REC-M as well.
Oh, you mean like this?
No. So the REC-M dot Z, and after that REC-M as well.
Sorry.
I don't.
Oh yes, sorry, yeah. So here I didn't add the M's, right? Thanks. Mm-hmm. Yeah, and here as well. Yeah. Okay. Yeah, so now it's a good exercise to define addition. Okay, so exercise. Define addition.
So the colon is the definition, and then, or how should this?
No, colon is just the type. So colon is just general. So if you see TROA, just think about it. Put it as T is in A. So A is some kind of set or type, and T is an element of it.
So REC-M N. So the N of REC-M is a function.
Yes. So just as every model has three components, right, written here, in the same way, every morphism also has three components, which have this shape. But this is just the usual notion, as Gergő said, this is just the usual notion of morphism for algebraic structures.
So what you're saying is that the value at here is that REC exists for any M uniformly.
Yes, exactly. And moreover, we have an extra condition. Okay, so I write it here. So we have an extra condition, which is this uniqueness condition. It's uniqueness. So there is only one morphism to any other. There is exactly one morphism to any other model from I. Okay. And with this uniqueness, this recursor becomes equivalent to induction. So if you have this uniqueness, then you can derive induction just from recursion. Okay, but this is late. We will only talk about this kind of stuff later, because now, okay. So this was just an example of an alternate presentation of natural numbers, where we first started with models, and then we said that the syntax is just the initial model. And this is exactly the same what we will do for type theory or for programming languages in general. Is that first we say what a model is, and then we will define the syntax to be the initial model. Yes?
So can we think of syntax as some kind of smallest model, because there is a morphism to any other model, so it has to be small in some sense, right?
Yes, you can think about it as a small model, yeah. Yeah, so that's but there's usually we also have a terminal model, for example, which is the trivial model, which for in the case of natural numbers, that's just the one element set, right? The one element set also has this structure, right? Because there's the one element set, it has an element, and then the S function just always returns that single element. And there is, in fact, a homomorphism. So that's another example of an interesting homomorphism. So another exercise is show that there is a unique morphism from any M to the model, which one element set, right? Lambda anything dot set, right, to this model.
I would say that the initial model is the largest model, not the smallest, but I guess it's just the point of view or different.
This is also sometimes called the free model or free algebra.
So I think it's not the largest model because, for instance, for sets, the initial set is the empty set, and
yeah, I mean not literally, but I think of it as something big and not something small. So it's typically you project and not inject. But this is just like a comment.
But
I
even
don't
for
really...
natural numbers, you have more natural numbers in non-standard models, no?
Yeah, that's why I asked the question initially, because I had the non-standard models in mind, like they are larger, and I thought that the usual are the initial model.
But okay, but this is just some kind of universal algebra stuff, so it's not extremely exciting. Yeah. But okay, let me add another exercise. So do the same for some well-known structure like binary trees with natural numbers at the leaves. Okay. Just think about how the real binary trees are the initial object in or the syntax or the initial binary tree model, and how does this relate to your usual idea of what binary trees are? Okay, and then sorry for natural numbers. Let me add another exercise. So maybe show associativity addition. Okay, maybe a simpler one is left and right identity laws of addition using the help of uniqueness. So if you do these exercises, then it will like help you become more familiar with this idea of syntax being the initial object. Okay, so now before going to type theory, I would first I will present a very simple language.
Sorry, I have a question. So in the language that you have defined for this example of natural numbers, there's no way to define functions. So what is addition? Like, how would I even define addition so that I can prove that it has a left and right identity?
So it will be a meta-theoretic function. So just as, you know, there is a function in the notion of homomorphism from the recursor, I can get out a function. I get out a function which goes from the syntactic natural numbers to some random set, right? And that's how you define addition, that you get a function from I to n to some other set. In fact, in this, for addition, sorry, where is for addition? For addition, I can tell you that m dot n will be I dot n arrow I dot n, right? Because then you get rec m dot n, it will go from I dot n to this particular set. And this is the type of additional natural numbers, right? It takes two natural numbers and results in a natural number. Okay, so this is the start of the solution to this exercise. And then in the same way, when you prove left and right identity, you will need to define a particular natural number model, or a particular model, which out of which you get, with the recursor, you get these identity laws. Okay, is that an answer?
Yeah, sure. So in that case, this model would be the one where basically the natural numbers are iterations of some functions or something like that.
Sorry, which model are you talking about?
Well, so the
this
okay,
one.
Yes.
Yes.
Yeah. I mean.
Okay.
Yeah, but okay. Sorry. Let's do a simpler exercise first. Define the function n maps to 2 times m plus 3. That's a simpler, because here I can tell you what these are very easily. So this is just natural numbers as well. And what do I do? Look, 0 is replaced by 3. So m dot 0 will be just 3, okay, which is, by the way, what is it? I dot s applied to I dot s applied to I dot s applied to I dot 0. Okay, and m dot s, it needs to be it needs to go from I dot n to m dot n to m dot n. So it will go from I dot n to I dot n, and it will be the function which adds 2 successors, because I want twice. So this will be the function lambda x dot sx, right? So here, in this algebra, you can think as what the recursor does. It will replace I dot n by I dot n. It will replace 0 by 3, and it will replace successor by 2 successors. And if you do this, so if you have s 0, okay, if you do this, then you will get, so every s is replaced by 2 successors. So this is the first one, this is the second one, this is the third one, and then 0 is replaced by 3, right? So this is what I will get. And here I have 1, 2, 3, 4, 5, 6. Yeah, so I get 9. So that's the correct result. Okay. So that's how it will work. And I mean, this comes out of recm. Apply. Okay. Concretely, recm dot n apply to this thing. Okay, I'll always imagine an I dot here. Okay. So by the way, this is what I described here for natural numbers. This is usually called the initial algebra semantics of natural numbers. And okay, the RIC and some more comments. So RIC is sometimes called fold or eliminator what else is it called? I don't know.
Iteration.
Thanks. Iteration or iterator. Yeah, this stuff. Okay. So first this was an example of natural numbers. Let me give a bit more programming language like examples, because natural numbers were very simple. So now I define a simple expression language. Where I will have two kinds of expressions, natural numbers and Booleans. Okay. So in this, a model is the following. I have a tie, which is set. I have a term, which is tie arrow set. So for natural numbers, I only had one set. Let me just write it here to compare. So it was n set, zn, and s, n arrow n. So now I have two sets. I have types, and then for each type I have a set of terms. Okay. Then I have two types. I have bool and not. Okay, these are in tie. And then I have some operations, like I have true, which is in bool, tm bool. Okay, so let me write it a bit more beautifully. Okay, then I have false, which is also tm bool. Then I have if then else, which takes a tm bool and some tm of a for any a and another tm of a and returns a tm of a. Okay, then what do I have? I have 0, which is a natural number. I have successor, which takes a natural number and returns a natural number. And I have is 0, which takes a tm not and turns it into a tm bool. Okay, and now this will be a real algebraic theory, so it will also have equations. So I will have some equation called, okay, let's call it bool beta 1, which says that if I apply ite to true and then u and v, then it's equal to u. Okay, then I have bool beta 2. It says that if I apply ite to false, then I get the second one. So ite is for if then else, right? This is usually called if then else in a programming language. And I also have not beta 1, which says that if I apply is 0 to 0, then I get true. And then I also have a not beta 2, which says that if I apply is 0 to successor of some t, then I get false. Okay. So now I claim that a model of this expression language, okay, usually this expression language is called razor. Okay. From Occam's razor, it's usually called Hutton's razor, because Hutton likes to study these very simple expression languages which are only there for illustrating something. So now I also call it Hutton's razor. So a model of Hutton's razor is a set, then a set indexed over that set, then two elements of this first set, and then these are the operations on the second kind of set on the family, right, which satisfy these equations. Okay, so this is a model of Hutton's razor. Is this clear? I mean, I think this should be some very familiar kind of very simple programming language where you can only write expressions. Again, as Gergő said, there are no functions in this language. But this is good for illustrating the purposes. And now the question is, what is the syntax of this language? And again, the syntax for Hutton's razor is the initial model. Okay, the same way as before. So we have an I. Okay, I is a model. I is the initial model, and we have this recursor which takes any random model M and gives you a morphism I to M, okay? And again, what is a morphism from I to N? So let me write down the types for this. So for example, recm dot I will go from I dot type, so from the initial type to types in this model M. Okay, and also let me write the one for terms. It will go from any term in the initial model, so any syntactic term. It will go into a semantic term where the A will be mapped to the result of this function, right? And I also need to say that it preserves all operations. So for example, I know that if I apply recm.tie to I.bool, then I get m.bool, okay? And let me give another example. If I apply recm.term to is0, I.is0 of some t, then I get m.is0, and then recm.tm applied to t, okay, and so on.
So basically, the beta functions are like semantic axioms?
Yes.
Ah.
But the interesting thing is that the semantic axiom, so this is what people, okay, so what traditionally people call this is usually called operational semantics. But now we give operational semantics as equalities. And this part, so these indices are usually what people call indices, are usually called typing relation. But in our view of programming languages, these are all included. And let me talk a bit about the syntax. So what is the syntax? So just as for natural numbers, the syntax was somehow the smallest but freely generated way of generating natural numbers. So we have some kind of syntactic zero, and we apply the syntactic successor finite number of times, and that gives us the syntax. And it's the same here. So in the syntax, we have the I.bool, okay, and I.not, and these are the only elements of I.tie, okay? So I.tie really doesn't have any more elements. Okay, but for I.term, we have I.term of I.bool and I.term of I.not. So these are the two sets, right, of the syntax. And then I have I.true and I.false. These are all in I.term of I.bool. And what else do we have in I.term of I.bool? For example, I also have I.if then else applied to I.false and I.false and I.false, right? That's also in I.term of I.bool. And let's also write some other thing. For example, I have I.0 of I.is0 of I.sock of I.0, right? This is also a term in I.bool, but there is some extra stuff, and the extra stuff is that some terms are identified, okay? So even in the syntax, some terms are identified. They are not completely freely generated, but they are kind of freely generated, and you can think about it as if there was a second step where we identify lots of different terms. So for example, here, this term is in fact the same as I.false, right? By this law, because this law applies to the syntax as well, because the syntax is also a model. Then, in fact, this term here, okay, so this term is just equal to I.false. So this is not really a new term. This is not a new term. This is equal to I.false. And also, this term is not a new term. What is this equal to?
Also I.false?
Yes, thanks.
Or
Yeah. In fact, can anyone tell me any other term of I dot bool? Something which is not equal to I dot false or I dot true. What do you think?
Something that is not true and neither false.
Yeah. But it's still in I dot term of I dot bool, so that is still a syntactic Boolean type term.
Is 0 t without specifying what the t is? Or do I have to choose a t for that?
Yeah, I mean, you need to, you need to specify the full term. So you need to say what t is, yeah. Okay, let me show you something. So one suggestion could be I dot is 0 of I dot false, right? Because I don't have any equation on this, right? Because if this was 0 or successor, then I would have a problem.
Yeah, but is 0...
because it would just be true or false. But what's the problem with this term?
It's incorrect.
Yeah, it doesn't exist.
It's not the right type, yeah.
Yeah, it doesn't exist because I dot is 0 only takes terms of type not, and I dot false has term bool. So we cannot write this down. In the same way, it's kind of, you can view it as the same way. So, okay. So, I mean, I leave it here. So, sorry, this cannot be written down. Okay, cannot be written down. In the same way as you cannot write down rubbish like, I don't know, successor of IT and this kind of stuff, right? So, this also cannot be written down. So, you can only write down things which make sense according to this algebraic structure. Okay, what about this other suggestion? So I say I dot is 0, and then here I use I dot ite, okay, and here I write something. What can we do with this? Because here I cannot apply any of these rules, right? I cannot apply not beta 1 or not beta 2 to this. Do you agree?
What's question mark?
Yeah, I write there something.
You want something from us as a placeholder? Okay.
Yeah, but just imagine there is something in the question mark, okay? And then what I'm claiming, I cannot use any of these equalities, right? So then I claim that this is a new term because this is not I dot true and not I dot false.
Well, doesn't it depend whether A is not?
A needs to be not, right? You're right, yeah. So very good. So A needs to be not. So in fact, these two things need to be not, term of type not, and this needs to be a term of type bool, yeah.
Yeah, but then we have already established that true and false are the only two bools, so you can use bool beta 1 and bool beta 2 to reduce it, to show it equivalent, sorry. To the second or the third argument.
Yeah, very good. Thank you. So in fact, here you would write I dot true or something like this. And here you write two natural numbers. And then this would be equal now by this first rule, right? This will be equal to the first natural number. So I don't know, question mark 1, question mark 2. So this will be equal to question mark of 1, right? And then you will be able to apply one of these rules because this is a natural numbers, and then you get either I dot true or I dot false. Yeah. So in fact, that's the sad truth that in this programming language, there are really only two terms of type I dot bool, right? So really only these are the two terms. All the other terms are equal to either this or that, right? So that's why this is very simple programming language. Yeah. And in fact, yeah. So we will see. In fact, for this programming language, I think you can just prove it. Yeah, it's very simple to prove this fact. It's very simple to prove this fact that I dot bool only has true and false, and the natural numbers are, so terms of type not in the syntax, they only have 0 and successor of a natural number. So again, there are no more complicated natural numbers in this language than than usual natural numbers, and this comes from all these beta laws. So these beta laws make it sure that any more complicated natural number will somehow simplify to 0 or successor at some point. Okay, and so as a next example, let us define some model. Okay, let's define some models of. Let's define some model of Hutton's razor. Okay. So, for example, first model. Okay, so my question is: can we extract a model? Can we define a model which, you know, every term is some kind of tree, right? And then lots of trees are identified. So a term is okay, it's either a leaf of a tree, like true and false and 0, or it's either a unary branching of the tree, like sock and is 0, or it's a ternary branching of the tree, like if then else. So, and then I say, can we calculate what is the height of the tree? The tree model. Okay. So so in this model, let's call it a model h. Okay, h for height of the tree. So h dot I, let it be the same as I dot tie. Okay, and h dot term of some type. I just want a natural number. Okay. And that natural number should give me the height of the term. Okay, every term is some kind of tree, either unary branching or ternary branching, and I want to calculate the height. So, for example, let's say h dot true. Now in this model, it will need to be a natural number, and I say it's 0, right? Because it's just a leaf, so it has height 0. So h dot false, it's also 0. H dot if then else of uv or tuv, okay, tuv. Now t and u and v are natural numbers, so they are all the heights of the trees for t and u and v. So here I would say that what's the height of if then else? So you can imagine, you know, here is h dot ite, and then it has 3 children, and here is u, here is t, here is u, and here is v. And then how can we calculate the height of this tree? We just take the height of t and the height of u and the height of v, and we take the maximal of these, and then we add 1, right, for this level. So it should be 1 plus the maximum of tuv. Do you agree? And similarly, I don't know what's the height of E0 of t is just 1 plus the 1 plus t, and so on. Okay. And now, if I am able to define this model, then from any syntactic term, which is, as we discussed, it's a tree where some trees are identified, I can get the height of the tree.
But wait, so this doesn't satisfy the if then else beta rules, because if then else will always have a height of at least 1, whereas true and false will have a.
Yeah, very good. Thank you. So for example, let's see, this law would say that height of ITT I dot true uv is the same as u, right? this is what I want, and h of it was this. So here, when I'm defining this model h, I would need to satisfy this equation, and this equation is not true for certain. Well, if t and v is 0 and u is 1, then it is not true, for example, and it's easy to find such t and v's, I guess. No, so so I won't be able to define this model. Okay, so
it's broken.
Yes, it's broken. I'm not able to define this model. And can someone give me somehow a reason for this, or what's the point? Because I mean, I thought that my syntax should be like the usual syntax. With usual syntax of a language, you should be able to find the height of a tree, no? Of an abstract syntax tree.
I think the usual syntax of languages isn't the algebraic syntax. It's only, well, at most a well-typed syntax. So yes, I guess you'll distinguish between different syntax trees, which are semantically the same.
Yeah. So here, this is a very important difference from usual way of thinking about syntax, that even in the syntax, we equate the kind of operationally equivalent terms. So we cannot write this model, which gives us the height of a tree. And similarly, for example, we cannot define a model which tells us whether there is a true I dot true in the term, right? This is another property. Whether there's an I dot true in a term, it's another property which is not preserved by our equalities that every model should satisfy. So, in fact, what kind of models can I even give? Can you give me an example of a model that would even work? What can I do with my simple Hutton's razor language? What would be a meaningful model?
Write an evaluator, for example.
Yeah, that's a good example. So let's give, this is what we call, and I already mentioned this, the standard or set model. So and this can be used, so the recursor into the set model or into the standard model is what people usually call an evaluator. Okay, so let's see this model. So in this model, so let's call it S for standard model, or no, sorry, let's call it M. Okay, so the types in M are sets. Okay, so every type becomes a set. Every term of some type A, which will become an element of that set. Okay. So in M dot term, in general, you know M dot term has type M dot tie arrow set, right? And if M dot tie is itself a set, then we can just return that set. Okay. So in our case, M dot term has type set arrow set, right? Because M dot tie was defined to be set by this first moment. Okay, so then what should be M dot not?
Well, the meta-theoretic set of natural numbers.
Yes, thank you. Yeah, so it will be the set of natural numbers. Then M dot bool will be the set of Booleans. Yeah, okay. now I write 2, so it's like, let's call it TT and FF. Okay, these are the meta-theoretic Booleans. Then m dot true will be just TT. Oh, let me write the type of m dot true. So m dot true has type m dot term of m dot bool, which is the same as n dot term of bool, and m dot term just returns the thing that we give it. It's just the identity function, so we just get 2 elements.
What is that symbol, by the way?
Which symbol? This?
Yes.
It's just bold 2
of a 2.
Yeah, 2. It's a 2-element set. It's like natural numbers is the infinite, countably infinite set, and this is the 2-element set.
But couldn't we simplify that in a fundamental way by saying that we're just going to have one set, because we don't need to be type safe in our modeler, right? The syntax should take care of that. So we could just say that 0 is true and 1 is false.
Yes, yes, we could do that.
Natural numbers, right?
Yeah, we could do that. I mean, it would, we could do that.
It would just mean that we have extra equalities, because now we would have an equality that true is equal to successor of 0, but that's not a
that's a very good point. And so we could just say, in fact, that I don't care about types, and I just say m dot term of, sorry, this is the 1-element set. Okay, the 1-element set of anything is just n. Okay, so I give this as an exercise, this model. And we could also do this model. Okay. I would be in trouble with this model if I also added I could add some extra equations, some kind of uniqueness equations. No? Oh no, but I don't have variables now, so. Oh no, okay, I don't know. No, I think this model just works, as well. Okay, but let's just finish this model. So true is just the TT, false is FF, then ITE of some TUV. And so if then else, and now I know that T is either this or this. So because T only is a meta-theoretic set, it only has 2 elements, so I just say if, basically I say if T then U else V, right? Where this is the meta-theoretic if then else, right? Which works for 2. So in fact, this is why we call it standard model, because it's standard in some way, or it's boring. Because what do? Natural numbers are mapped to meta-theoretic natural numbers. Booleans are mapped to meta-theoretic Booleans. True is mapped to meta-theoretic true. If then else is mapped to meta-theoretic if then else, and so on. So this model doesn't really give any new fundamental knowledge, or what this is. Some people call this the Tarskian semantics, because as an analogy with logic Tarskian semantics, where I just say that true is mapped to true, false is mapped to false, this junction is mapped to this junction, and so on. Right? But let's check if this model really works, because we had some previous model which didn't work. Now we hope that this one will work. So let me just write. Oh yes, let's check the equalities for if then else. So bool beta 1 says that if I apply this to m dot true, then I get u. Okay, so let's see if this is really true. So now I replace m dot ite by this, where t should be m dot true, right? But m dot true is defined as the meta-theoretic TT. Okay, and this law now holds because of the meta theory, because this law should hold in the meta theory, right? If then else is defined properly by our meta theory, then this law should hold. So this comes from the meta-theoretic beta law for if then else. So you see, this law is even boring in the level of equations, because all the equations just hold because of their corresponding meta-theoretic equations. And it's the same with the other equations you can check. Okay? Oh, okay, right. And now we have this model, this standard model, and we can use the recursor. So rec of m takes any term of say m dot bool. Sorry.
You mean rec of m of tm? Rec of m
yes,
dot
thanks.
tm.
Yeah. So it takes any term of type bool and it turns it into an m dot tm of m dot bool, right? So let's just see, m dot tm was just the identity function, so this will be m dot bool, and m dot bool will be just 2, right? This is how I can turn any term to a meta-theoretic Boolean. Any Boolean term to a meta-theoretic Boolean, and similarly, if this is natural numbers, then I get a meta-theoretic natural numbers, and this is the interpreter, okay? Where I get something in the syntax of my programming language, and I get something in my meta-theory. Okay, this is called interpreter or evaluator.
So what is the meta theory? That is our conceptual understanding, or is it another model?
Yeah, it's our meta theory. It's mathematics, right? It's the language in which this file is written, where I can write arrow. This is part of the meta theory, but sometimes more recently, the meta theory is another programming language like Agda or Coq, because people like to do meta theory of programming languages inside another programming language. Right. So, in fact, my notation that I use for the meta theory is very close to Agda's notation, because that's the programming language that I'm most familiar with. But here you could write some other symbol for function space. Here you could write some other symbol for sets. Okay, if you are in set theory, you could have written this or any other notation. Okay. Okay, and then so here the exercise is to exercise finish this model, and here in another exercise define the C-style model, okay, where true is equal to 1 and false is equal to 0, and any other natural number is also true, say, or something like this. You cannot, because for if then else you need to say how it works on any natural number, not on 0 or 1 in this model. And, yeah, okay. Okay, so.
Sorry, just a quick question before we go move on. Would the rules also be satisfied in, for example, a trivial model where everything would be mapped to the same thing? Let's just say the natural number 0.
Yes, so this is the trivial model, right? An m dot term of anything is also just the one element set. Okay, let's call the one element set is the thing which only has star in it. And then all the operators are just star, right? M dot false is also star. The types are also just star. Everything is just star. And obviously all the equations are satisfied because star is equal to star, right? TUV is also just star. And then m dot beta is bool beta 1 is obviously true because it's applied to m dot true is equal to star, but star is also equal to u because everything will be just star. So okay, maybe you need to do some work to see that this u is also star, but because it's
Okay, thanks.
Okay, any other questions? So just to summarize, so we looked at initial algebra semantics of natural numbers, and then Hutton's razor.
I think we should mention that algebra is a synonym of model.
Oh, yeah. So algebra, when we say algebra and model, they mean the same. Yeah. And what else? Okay, yeah, and Hutton's razor language, and we covered interpreters. Okay, and let's just write. Yeah, so we covered interpreter, which is the same as evaluator, which is the same as the recursion into the standard or set model. Okay, we have algebras and models, and we have morphisms or homomorphisms between models. And as the recursor was also called fold and iterator and eliminator. Okay, so one topic that we didn't cover, we didn't look at examples for uniqueness, but we will later look at this. Okay, and now the next step would be that we look at the real programming language that we want to look at, which is type theory. So next steps. So first, what is a model of type theory? And then obviously the syntax of type theory is the initial model. And in fact, so for the type theory, if I don't use this second point and I try to define the syntax of type theory, not in the algebraic way, but in the usual, like traditional way with typing relation, operational semantics, then it becomes ridiculously complicated. And it's basically unfeasible to do meta theory of type theory not algebraically. And for other programming languages, it's simpler to do the non-algebraic description, but I think it's still better to do the algebraic description for other languages as well. Okay, so are there any questions? You can also, or comments, you can have comments. You can also have general questions about the direction. You can also say some comments about whether this was too slow, too fast, where you got lost, or something like that. Because now we will move on to some next big topic.
So I do have a question. Is that in this case, the term model that we had, or the syntax or initial model or whatever.
Yes, this is another,
is just completely isomorphic to the standard model in our case, right?
Yes, for this simple language it is, yes.
Yeah, but that will not be the case in general, I suppose.
Yeah, that won't be the case in general.
That makes sense. Thank you.
So usually it's already not the case in this second version, in the Gergő style, C-style model. It's also not the case because this model has more equations than the syntax. No, for example, we have in this model that m.true is the same as m.successor of m.0, right? And usually for type theory or for more complicated programming languages, we will have this phenomenon, for example, and other similar phenomena. But I never thought about this question that you just asked. So.
are the standard set model and the syntax actually isomorphic? Because I think there are more types in the standard model than there are in the syntax. So like.
Oh yes, you're right.
So
we need to restrict the time. Yeah, you're right. We need to restrict the types, because here we said set, so they are not isomorphic. Yes, you're right.
Yeah, but we can
terms
change it
are
to
isomorphic,
bool.
but not the types. Yeah.
But we can change it to bool, and then it's really isomorphic.
Yeah.
But then,
so in fact, we have a paper about this problem, which is called "Shallow Embedding of Type Theory is Morally Correct," where we show that the syntax of type theory is the same as a certain kind of standard model. But you need to do this kind of tricks that András just said, that, for example, you need to replace types by some syntactic, like bool, or some syntactic representation of types. Yeah, but it's a very good question. So in fact, the answer is that for type theory, we have a variant of the standard model, which is isomorphic to the syntax, in fact. And you can use this for easy formalization of type theory. Okay, any other questions or comments? And is it okay? So when should we finish? Should we finish at 2 or should we finish at 1:30? That's a question. I don't mind.
I don't mind.
Personally, I'm free until 2, so.
Okay, so let's try to do it until 2. We will get very tired by 2 anyway, and we will see how it goes. And we are recording it, so for those who got lost or who don't understand something, you can also watch the recording later, but I encourage you to instead ask questions all the time. Okay, so now model of type theory. And so this model of type theory has another name. It's called CWF. I mean, just as, okay, a model of natural numbers doesn't really have, you could call them Peano algebras or something, but like a model of group is the same as a group. So in the same way, we have a name for a model of type theory, which is CWF, which abbreviates category with families. So this is a categorical description of a model of type theory because it starts with category with families, but you don't need to know category theory to understand it. So I think we will introduce some necessary category theoretic concepts, but even without that, you can understand what's going on. So just as before, we have terms. Okay, so terms were previously of type tie-arrow set, and okay, we had types, but now we also have variables. So in fact, we want to say that we want to say things like, okay, let's say, so for example, if x is a natural number, then lambda y dot x plus y is a function from natural numbers to natural numbers, right? So in fact, this is some usual notation that people sometimes write. And what we will write instead of this will be like this. So this is a term in this context, which has this type. So this is what we will write. So terms will be indexed not only by types, but also by context. So terms will have this shape. So con arrow, tie arrow set, and then obviously we need context as a set. Okay, and then another thing which comes up when we do when we really have variables and lambda abstractions, and when we are in lambda calculus, is that we want to satisfy the following equation. So if an application is applied to some term u, then this is what is usually called beta law in lambda calculus. This should be the same as t, where x is replaced by u. Okay, this is called beta law for function space. Okay. So we need to be able to express these kind of substitutions. To express this, we will introduce a notion of parallel substitutions. So parallel substitutions. And these will go between context. So in fact, what we will write here is that every variable, I call it ID, because every variable is mapped to itself. So this is the identity substitution, but x is mapped to u. Okay, this is how we will write this. So we will have another sort of substitutions which goes between two contexts. So substitution goes from one context to another context. So let me briefly introduce what this is. So let's see. So we have a substitution which goes from y and let me write instead of n, let me write not bool z bool to a in bool and b in not. Okay, so what is a substitution from this context to this context? Okay, so maybe I didn't say that a context is obviously a list of variable names and types. Okay, so it's basically a list of types decorated with this variable name. So this substitution is given by two terms which give the value of a and b. So for example, a substitution here will say that a maps to I and b maps to if z then x else 3. Okay, this is a correct substitution because this substitution gives the value of all of the types in the target context using the values of the domain context, right? So this used y and it also used z and it also used x, but in fact it doesn't need to use all the values in the domain context. So I could have said 1, okay, or something like that, and it's still a substitution from here to here. Okay, so this is the intuition for substitutions, and it's a kind of a practical experience that when people try to define models of type theory or programming languages in a nice way, then they always need these kind of parallel substitutions and not only point substitutions. So this usually people only write one substitution here because for this operation I only want to replace the value of only want to replace x by something, but to do any kind of meaningful proofs about this system, you need to introduce these parallel substitutions. And
I might be too stupid for this, but what is the line above which you have the cursor in, so that x is n and then that rotated top? And the
oh yeah, so if you haven't seen this notation before, then just ignore it. So this is the usual way. Okay, this is how it's parenthesized. So this is usually people define type systems using a ternary relation, which is denoted like this, and this is called turnstile. So with the turnstile, and this is the typing relation. So in some context, some term has some type, but we won't use this notation. Instead, we will always write this. Okay.
So lambda y to x plus y is a function.
Yes.
Is a bivariate function which needs the x to be bound, basically.
Which needs X in scope, yes. It refers to a free variable, which we call X, yeah.
Okay.
Also, could you explain the notation one line below that T and brackets?
This?
Yes.
So this is a general notation for saying this. So this is a general notation for saying that T, where all occurrences of X are replaced by U, okay? This is a notation like for this.
Search and replace in text.
Yeah, kind of. There are some subtleties, but I don't want to discuss those subtleties now. Yeah, and this is the intuition. Okay. There are some subtleties because there might be some bound X's. You know, inside T there might be a lambda X somewhere, and then you don't want to replace those and that kind of stuff. But yeah.
And the
other have to be scope.
I have also another basic question that the difference between lambda and functions is basically that with lambda I can have a dependent, not domain, but where I map to can be dependent on my input, right? Or is there any difference at all?
No, there is no difference at all. And this is not the main point. Because you can have lambda also in non-dependent type systems, and in fact we haven't discussed dependent types yet. So the first thing is parallel. Okay, so we have parallel substitution. Oh, I already written it here. So this is an important point that we have parallel substitutions. So this is some kind of new thing compared to the previous expression language. Okay, the zero thing was context, right? We have context, which are giving the list of free variables, a list of free variables of the types of free variables, right? Like here in this expression, there is one free variable, it's the X. So the context needs to mention what the type of that X is, right? And this then the type of the whole expression itself is a unary function from n to n. Okay, or sorry, I should have written not to not, because now we are talking about our object language, and in our object language I want to write more explicit notations. Okay, so 0 we have context compared to the previous one. Then we have parallel substitutions. So we have this sub, and we have this bracket, which is an operation. So we have an operation like this, which is notated like this. So given a term in some context delta of type A, and the substitution from gamma to delta, usually contexts are abbreviated by these Greek characters. Then I get a term of gamma of type A, okay? Like, let's see, so this is contravariant, that's important, contravariant. So you see the sub goes from gamma to delta, but the function goes from terms in delta to terms gamma. So let's see an example of using this substitution. So now if we have a term which is in some A bool, B not, we need a term in this context. So let's write, I don't know, if A then B else 3, else 1, okay. This is a term in this of type not. Do you agree? So this term has two free variables, the small a and the small b. So in the context, I mention what the types of these three variables are. And then the type of this context, it always returns a natural number, right? Because it's here it returns a natural number, and here it returns a b, but b is a natural number, so that's fine. Now what happens if I substitute this term? So, okay, so what is this term? it just returns either B or 1, depending on the value of A. So if I replace this term, if I apply this operation here on this term, and I put this substitution in here, then I should get a term now in this context, right? Because this substitution goes from this context to this context. So now gamma, this is gamma, and this context is delta, right? So this will be a term in gamma of type not, okay? And now gamma is this, so I can just replace this by this, okay? No, in fact, I don't replace because it's unreadable, okay? So it's a term of gamma of type not. So gamma has x and y and z as free variables here, okay? And then I will also want some rules on how exactly this substitution happens. So in my notion of model of type theory, I will have a rule that this thing is equal to what? I replace A by Y. So if Y, then I replace B by this and this, else 1, right? This will be the result of my substitution. So just as in my Hutton's razor theory, I had some rule for not beta 1, which said that is0 of 0 is equal to true. 0 is equal to true. Here in my new calculus in CWF, in category with families, I will have a rule which makes sure that substitution behaves properly like this, okay? So I think this will be, in fact, for this series of seminars, probably this part is the hardest, where you need to get used to these substitutions and notations and how you write down these substitutions. So yeah, I should give lots of exercises on how to understand these. Okay, so we have context, we have parallel substitution, and then another important thing is that we will use De Bruijn indices, okay, instead of variable names. So the point is, variable names are, as I mentioned, defining substitution with real variable names, it's extremely complicated, and it's much easier to use natural numbers instead. So what's the idea? So if you write lambda x dot lambda y dot x plus y, this function, right? So this will have type, okay, if x and y are natural numbers, then this will have type, yeah, it's a function which takes a natural number and returns something. And what is this something? This takes another natural number and returns a natural number, right? So this is the type of this. Okay, sorry, I should have written this. So this is a term in the empty context. So by dot I write the empty context because there are no free variables in this term. Okay, but now the point is that the names of bound variables don't matter. So this term is exactly the same as this term where I renamed this to Z, right? It really doesn't matter what the names are. So in fact, what really matters is that this Z points to this lambda. So in fact, it's some kind of, these are some kind of pointers, right? So Z points, okay, how do I draw this? Z points to this thing. I should have drawn like this, no? So Z points to here. This is important. And also it's important that that Y points to here, that one, right? So that's the important information, and the important information is not that it is called Z or Y. No, it's the same kind of thing with, this is a general thing with binders, like if you write in C, you write a function int f int x, and then here you write return x plus 3, right? This is a correct C function. This C function should be exactly the same as the one where I call this Z. Right? And in the same way, we have binders in mathematics, like say sigma I equals sum of I from 1 to 3, and I say 2 times I, right? This mathematical expression is exactly the same as this one where I use J instead of I, right? This is the idea of binders. Okay, so enough talk. So this we will notate instead of lambda z lambda y z dot y. Instead of lambda, we will write lam to emphasize that we are in the object theory and not in the meta theory. And another difference is that we won't write variable names. Instead, we will write numbers. So here is another lambda. And then here I need to write something plus something. And the somethings will say how many binders do I need to step to reach my own binder. So this is the zeros binder, and this is the first binder. So this will be 1 and this will be 0. Okay. Now this is a much easier way to treat variables, because now I don't need to state any equality about names, right, and renamings, because I don't have names anymore. I only have natural numbers. So there's only one way to write down this term now. Previously, there were infinitely many ways to write down this term, depending on the choices of variable names, and now I can only write this single term. Okay, is this clear?
As long as the binders are coming in the same order. So if I swap the lambda out, so I swap the plus, and then I say, okay, the outermost function takes a variable y, and the inner one takes z, then...
Yeah, but then it will be really a different term. So then it would be lam of 0 plus 1. And then I want to distinguish, because these terms are different, right? Okay, maybe if I know that plus is a commutative operation, then they are in some sense the same, but a priori I don't know that plus is commutative, so they are just two different terms. And I really want to distinguish these two different terms, yeah. Okay, so up to now, so we had context, we had parallel substitutions and this substitution operation, and we have De Bruijn indices instead of variable names. And then there's a third big difference from what we have previously, which someone else already mentioned before, is that we have dependent types. Okay, so this means that I want to be able to write types like this. For every natural number, I want to prove that I want to provide a vector of types of bool which has length n. Okay, so I have types like this. So vector takes basically it takes a type, takes a term of type natural number and returns a type. Okay, so this is what I want to be able to write down in my syntax. Okay, I want to write down something like this in my syntax. Okay, so so this means, and I mean, this kind of types are it's not possible to write this down in usual programming languages. The usual programming language don't really have dependent types or have some very limited form of dependent types like polymorphism. And this also complicates my algebraic theory. So let me now summarize what we have. We have context. Then we have substitutions between contexts, which are these kind of lists of terms, right? This was a term, this was another term, and we always have that many terms, as many components are there in delta. Okay, so let me just write it as a reminder that sub gamma A, B, C is same as Tm gamma A, and then a Tm gamma B, and then a Tm gamma C, right? Okay, and now types. So as you see, types can depend on terms here. So for example, this type includes a free variable. So types can also include free variables. So not only terms need to depend on context, but types also need to depend on context. So types have this specification. So for every context, we have the type of context, we have the set of types in that context. Okay, so Ti gamma is a type, or A, which is in Ti gamma, is a type which can have free variables in gamma, right? Okay, and then we also have terms. So terms for any context, and the type, we have the type of the set of those terms. But because types are indexed by context, there is some dependency here. So in fact, terms are given by a meta-theoretic dependent types. So terms are given for any context, and the type in that context, I have a set of terms of that type. Okay, so this is how, and these are the four sorts. So like natural numbers had one sort, Hutton's razor example expression language had two sorts, types and terms. Now, because we have variables and substitutions, we need con and sub, which are two additional sorts. So type theory has four sorts. These are the four sorts. Okay, and what are the operations? So I wonder what order I should use, but let's just write the operations which we heard before. So we have this kind of operation, right? Now this takes a term. So we have this substitution, but in fact we have substitution both for types and terms, because types can also contain free variables, so we should be able to substitute types as well. So if I have a type in delta, and I have a substitution from gamma to delta, and I have a type in gamma, and again, if I have a term in delta of type A, and then I have a substitution from gamma to delta, then I have a term in gamma of type A, but now this A is not in gamma anymore, right? A was in delta, because to even write down term delta A, I need to know that that type is in that context, right? So this, what I wrote here, doesn't make sense, but this is where I need to use this previous operation. So this is a term of type A in sigma, okay? So you can see that the substitution of terms is some very dependent operation, because, okay, I go from a context term in context delta to a term in context gamma, but also the type is substituted at the same time. Okay, so these are some operations. And about context, so I always wrote, so previously I wrote the empty context, like where was the empty context? Here, this term was in the empty context, so I need to know that this empty context is a context. Okay, I also have the empty substitution, which goes from any context to the empty context. That's just the list of 0 terms, right? This is the empty list, basically. There are no terms in the empty substitution. And then I have this comma operation, which takes, which adds a type at the end of a context. Like here I had A, B, C, right? So whenever I build a context, I start with the empty context. So I should have written this here. I always start with the empty context. Then I add the type, then I add another type, then I add another type. Okay, So it should be a con, arrow tie, arrow con. Right? This is like, if you think about lists, this is like the empty list, and this is like cons. It's for lists. In Haskell, it's written like this for some reason.
Yeah, but it's more like SNOC in Haskell.
Oh yes, yes. SNOC, it's the other direction. Okay, SNOC is just written cons in the other way because I add the type at the end of the context and not at the beginning. Okay, and similarly, so I have the empty substitution, and I also have another comma. It's usually also written as comma, another operation which extends the substitution. So if I have a substitution from gamma to delta, and then I have a term in gamma of type A, then I should get the sorry.
In the context extension, the context of the type is missing.
Yeah. Okay. Yes. Thank you. So in fact, this was a right. So I don't have types. I have types in certain contexts, and then the point is I can only extend the context with the type in that context. So this needs to be gamma. Okay. So all of these small considerations, like this one, these are quite, I mean, hard to digest, and they need some examples, and I will show an example in a second. Oh, okay, sorry. Before doing substitution extension, I just show an example. Like, let's write this context. So I have a x, which is a natural number, and a y, which is a vector of bools of type x, right? So this is an example of a dependent context, because this type only makes sense in this context. This type doesn't make sense without that context. Or if I have equality types, then I can write these kind of things. Then I have z, which has type. I have an equality of natural numbers between x and 3, right? So z basic. So here now I am in a context where I have a natural number x. I have x many booleans, and then I also have proof that x is equal to 3. This is how you can think about being in this context. And you see that. Sorry?
How do you mean I have already proved that x is 3?
I have an assumption. So this is an assumption, a free variable which has this type. So this is another dependent type that I haven't shown before, equality type, with which you can express equality of terms.
So it's not a predicate. So it doesn't mean that z is a bool, which is true if x is 3. But I know that x is 3.
Yeah, it's not. Yeah, you can think about it more as it's just a type. It's just another dependent types for which we will have terms. Okay. Later we will have rules. Later I will show the rules for VEC and for EQ. But for intuition, okay. I mean. Okay, maybe I just showed some very little intuition. So nil is a vector of any type of length 0, right? And then cons, if you have an element of type A and then you have a vector of A of length n, it gives you a vector of A of length successor of n. Right? These are the ways to construct vectors. These are the rules to construct vectors. And what's the way to construct an equality? So reflexivity takes A, which has type A, and then gives a proof of EQ of A of small a and small a, right? This is the only constructor for the identity type, or for this equality type. We will see later in all details these type formers, but now if I am writing it with variable names and kind of meta-theoretic notation, then this is how I would write these. Okay, so let's just see, how do I write this now properly? So the natural number is a type in the empty context, so I can start with the empty context. Then I have this vec bool x, which will be written as vec of bool of 0, right? And this is not a type in the empty context, but it's a type in empty context extended by 0. Okay, so now I can write it here. Okay, and now this is my next type. So let's see. So EQ n x3 and okay. Instead of 3, I write successor of successor of successor of 0. Okay, because then we can confuse 3 and the variables. Okay, SSS. So this is a type in empty comma n as well, right? But here I have a problem, because here I need to have a type which is in this extended context, because this type that I want to write for the question mark, okay, so question mark needs to have type, and I need a type in here, right? And why? Oh, sorry, there's the, I wanted to write this as well. Yeah, so, oh yeah, and I wanted to write not instead of this. So why, okay, so why does the question mark need to also depend on vecbool of 0? Because this type might refer to this vector y as well. So this type doesn't mention y, but it could mention y. So I don't know. I mean, I could write, as an example of how it could mention y, I could write EQ n of x and the length of y, okay? Where the sum, let me write, sorry, sum of y, where the sum, not the sum of y. The sum of booleans is not a natural number. What should I write?
The number of truths in y.
Okay, the number of truths in y. How many true values true are there in this vector, right? And now this type can refer to x and y as well. So what I need to do here, so if it refers to both x and y, then this would be 1 and this would be 0, right? Because this is the first variable, this is 0, and this is the second variable, one further away, so it's 1. So here I will need to write EQ not of 1 of SSSZ, okay? And this is how I built this context using this operation, okay? So when this is called, this is what they usually call weakening. So this type is meaningful also even in the context where I only have a natural number, but I need to weaken it to this context, right? Where I not only have a natural number, but also have a vector of booleans. And this one says that I don't care, so I just step over this first variable and I refer to this second variable. Okay. Okay, so this is how contexts are built.
So the numbering is always from the current position in the context backwards.
Yes.
So it's not the absolute index from the left, but rather.
Yes. Yes. This is just tradition that we extend the context to the right and not to the left. Yeah. If it, yeah. Because this is a SNOC operation, so we always have types at the end, so that will be always 0. Yeah. Okay, and I think it will be illuminating to look at the rules for function space. We will look at it in a second. Because then you introduce with lambda, you always introduce a new variable at the end of the context, and you can refer to that as well. Okay, so what do we have so far? We have the empty context extension, and okay, we have the empty substitution, and now we also want the extended substitution. So we want to go from, right? So if we know how to provide delta many terms, right? Sub gamma delta has a length of delta many terms in it. It's a list of delta many terms. And then I have another term, then I will have a substitution which goes from gamma to delta comma a, right? So I add one more term. But now there's a problem here. right? Because if I want to write down this, then this term needs to have type A in context gamma, but if I want to write down this, then A needs to be in delta. So this is not correct. Something is not type correct here. I need to fix this. So I don't know. Here, you know, when I write, by the way, I haven't mentioned this, but when I write down this operation, you know, it has two arguments, a substitution and a term, but in reality it has more arguments because it also has the gamma, the delta, and the A as implicit arguments. So sometimes people write it like this, that I have a gamma, which is in con, then I have a delta, which is also in con, then I have an A, which is a tie in something, and then I have this. And these curly brackets, at least in Agda, they denote these arguments that I don't want to write out because it's unnecessary complication. And you can always infer what those arguments are. Okay, so where should A be? So let's try. What if A is in gamma? If A is in gamma, then this is correct. Okay, but this is not correct. And A, the only way to make it correct is to substitute A, right? So to write some substitution here, which takes A from being in delta into gamma, right? And I have one substitution, which is this, but the problem is that this substitution goes in the wrong direction, right? So let's see. So A, if it's in tie of gamma, and sigma goes from gamma to delta, then A sigma cannot be applied. It only goes the other direction. So if A is in delta, and then substitution goes from gamma to delta, then A sigma is a type in gamma, right? This makes sense. So the point is that A shouldn't be in gamma, but it should be in delta. And then this doesn't need to be substituted. This is just A. And here, this A needs to be substituted. And you can talk about a lot about why this. So, okay, so now I put this here as remarks as for the. So here there are some implicit arguments. And here you can think about why, if I want a substitution, and I want to add another term to that substitution, then the type of that term depends on the substitution, right? And this makes sense. Okay, maybe we should look at an example for why this is the case.
So instead of swapping out the type space, at the end, we instead apply the substitution to the terms first, and then we are in the right type context.
Yeah, then that's the only way to make this operation meaningful. Yeah. So, for example, let's do a stupid example where I have a substitution from gamma to, I don't know. Let's just write empty natural not and bool, okay, and then I want to add the term, and then I want to add the term in empty of type, let's say, vec of. Let me write variable names because it's a bit more readable. So what I can do is, if I have a term in empty of type vec of bool of x, okay? This makes sense, in fact. So if I have because in the end, I want a substitution from empty to this, right? Comma vec of bool of x, right? So the term that I extend with can have a variable in it, because in the end we build a context like this. And now here is the point that this is not correct what I wrote here down. And this is why I need to substitute with the previous substitution. Okay, so here, which is this sigma, to obtain such a term. So let's see an example. So let's say sigma says that x is mapped to 3 and y is mapped to true. Okay, and then I want the term, and the term needs to be in the empty context, and its type needs to be, right, term of this in the empty context. So this thing needs to be substituted by sigma, and then sigma says that the value of x is 3. Okay. So now I know that the term that I need to write here needs to be of a vector which has length 3. So I can write here, I don't know, true, false, true, or something like that. That makes sense. Yeah. And now I get a new substitution which maps x to. This is how I can build a substitution. It's really x to 3 and y to true. And I don't know, z. Yeah, let's call this z. It's mapped to this this vector here. Right, and now it will be a substitution.
And this is of type.
Yes, exactly. So you see that the type of the third term, which had a variable in its type, has to be substituted by the previous substitution. So this is why these substitutions are not really lists. They are like lists, but you see that the cons constructor for the list is this dependent type, where the type of the second thing depends on the first thing. And this is a subtlety that you have when you have dependent types.
Why was I allowed to write sub of nothing or sub of empty set for the third statement? I built the substitution with an existing sigma. So why is it not part of the type of the bottommost statement anymore? One below.
Here.
So why is that empty set in the first type argument? So why is it sub empty set?
Here.
Sub nothing. Yes.
Because none of these terms have free variables, right? So they are all meaningful in the empty set.
So I constructed a substitution that doesn't have a parameter or doesn't have an unbound.
Yes, exactly. So this is a substitution. You can think about it as a closing substitution. So this is something that that constructs, gives the values of the free variables of some term, and then that term can be run. So usually the terms in the empty context, those are the ones that people call actual programs that you can run, because they don't have anything any moving parts. Okay, so you see that this substitution was constructed.
What if I wanted to construct a substitution with like the previous one, but the final type I want to be such that the z variable in the substitution has type vec bool and 3. So the x is so instead of x I write 3.
Yeah, that's also valid, and this substitution would also have that type. Could also have that type. There's no difference.
So it's the same syntax. If I want to write that substitution, so one syntax can have multiple.
Yeah, so you want a substitution which has type 3, right? In fact, now I write it as list because there is no dependency here. So here these are all closed types. So this would also work in simple type theory. So here I don't even need dependent types, but yeah. But the same substitution would also work here. If you say x should be 3, y should be true, and z should be
but it's
true,
not actually the same substitution. Because
if I change, but for example, if in the previous one I changed x to 4, then it would break.
Then the third component wouldn't be well typed anymore. Yeah. And as András said, sorry?
But if I change x to 4, but z stays the same, then the second example still works. So it still has a type sub from empty to not bool and vec bool 3.
Yeah, this is also correct. Yeah, you can write anything here. Yeah.
So what happens here is that the two so when we had the example when the substitutions looked the same, they are not actually the same because there are some implicit arguments.
Yeah.
And the implicit arguments are different, but we just usually don't write them out. So the two are different because there is a type involved in the extension of
you
the
see here, this is this implicit argument
Yeah,
here for the extension, which is different for the last comma. Yeah.
And in the first example, I write vec bool of 1 for the type.
Yeah.
Because the length is depends on the first variable in the context.
Yes, exactly. And here you just wrote, exactly. Yeah. But so the point is that you should remember is that a substitution is a list of terms, but the terms have these dependent types. So the first term was term empty of not. The second term was term empty of bool. And in fact, here bool was substituted by the first term. So let's call it T1 and T2 and T3. But because there was T by epsilon comma T1, but because bool is a closed type, it doesn't care about substitution. So I just mentioned that for bool, we have this rule that bool substituted by sigma is just bool. And then T3 was a term empty of vec bool of 1, right? So I write V1 for variable 1. And then it was substituted by epsilon comma T1 comma T2, right? But now this type was equal to so this V1 was substituted by T1, which is T1, right? So this is how it works. So in a substitution, the types of the later terms depend on all the terms before the previous, or can depend on the other terms before. Okay. So I think time is up. So let's close it's over for this week, and we continue next week. So we still haven't finished all the rules for CWF, and so the exercise would be to write lots of different interesting substitutions, okay, and understand what the structure is of substitutions, that the later things depend on the previous things, and so on. Okay, and also another exercise is look up CWF. What is the definition of CWF? It will be a bit more stuff than what I wrote up to now. Okay. Okay, are there any comments or
Oh, I do have a question if there's still time.
Yeah.
Right.
But, So, but feel free, anyone, to leave and whatever. Yeah. Yeah. What's the question?
So my question is about when I give a model of type theory in the future, maybe 2 lectures from now or something, will this substitution be a thing that I define per model, or will substitutions and context be this constant thing that they can only be one thing essentially?
It will be defined per model.
All right.
But there's also something called contextual models, where you fix that contexts are given by lists of types. So where contexts have a inductive structure superimposed on them, and that's like a subset of models, but not all models are contextual, and in particular the standard model is not contextual, that we will first look at. So
Sure.
people study both versions, but in fact our notion of model will be very simple. It will be just algebra for a CWF, and that's it.
Okay, that makes sense. Thank you. Will we have equations for substitution then? That we'll have to obey, right?
Yes.
Okay, good. Thank you.
Yeah, so the category part in categories with families will be an actual category which already includes substitutions, because substitutions will be the morphisms in the category. Okay, any other questions?
I have two technical things. First of all, whether this file will be available somewhere, and if so, where?
I will put it in the típuselmélet seminar Teams group.
Okay. And the second one would be to discuss the suggestion that arrived in the chat meanwhile, that it would be probably more readable if there was a distinction between natural numbers and De Bruijn indices. So maybe those circled numbers could be used for De Bruijn indices that has been suggested.
Yeah.
For the future.
Yeah, or we could write a V in front of each De Bruijn indexes, no? And then it's V for as variable.
And then you could no, I really like these circle numbers or some other kind of.
Yeah, but but brackets are used for other purposes as well,
No, but
it's not bracket. There is Unicode symbols for all kind of things, and Agda mode seems to support it.
Oh, okay, yeah.
On a blackboard, I usually underline or something, but there are many Unicode possibilities. So just you can try this.
How do you write a circular number?
With two parentheses.
Number.
Oh, I
and
see.
then
press right.
Okay, I see.
And there are many variations like inverse, so white on black, if you press right more times.
Yeah. Okay, so I will upload this file, and if someone wants to volunteer, can replace all the De Bruijn indices with the correct circles. Yeah. Okay, wait, I call it sam1.txt and upload it to this chat to the meeting chat. Okay. Okay, then see you next week.
So I'm going to be the next lecturer next week.
Yeah.
Okay, so just continue from here.
Yeah, so you should introduce all the parts of CWF, I guess. Well, yeah.
Okay.
Yeah. Okay. Good. And okay, I stopped the recording now.